Today we explore the intuition of depth-first search. Let us begin at our first node, labeled A. From A, the graph branches out to two neighbors, B and C. Node B also has its own child, node D. In a depth-first search, we dive as deep as possible, traveling from A, then to B, and finally down to D. At this point, we have reached a dead end because there are no more neighbors to visit. Since we can go no further, we must backtrack to the previous junction. Now that we are back at node B, we find a new path to node E and continue our search. This process is defined by a simple recursive logic, where for every neighbor found, we immediately call the search again. Under the hood, this algorithm uses a stack structure. As we visit nodes A, B, and D, we push each one onto the stack to remember our current path. When we hit that dead end at node D, we pop it off the stack to return to the last node that had unexplored neighbors.
Welcome to the Stack and Depth-First Search. This container holds our data. We begin with 3 items ready for processing. We add them one by one. This is the last in, first out principle. A push operation places the root node onto the top of the stack. To retrieve data, we pop the top item off and back into our workspace. Let's apply this to a graph. Here are nodes A and B. We visit A and push it onto our stack to track the path. Moving to B, we add it on top as the search goes deeper. We pop B to backtrack, returning to A to look for more nodes. Recursion does this automatically, using an implicit call stack to manage nested functions.
Backtracking is a technique used to explore paths through a tree to find solutions. We start at the root and move down a branch to reach a leaf. If we hit a dead end, we mark it and move back up to try the next path. We continue this until every node is explored and we return to the start. To understand performance, we label nodes as vertices and connections as edges. The time complexity is big O of V plus E because we visit every part of the structure. The space complexity is big O of V, which represents the depth of the recursion stack. This provides a complete summary of backtracking efficiency.